Hello. So I am Pierre Deling, emeritus in the School of Math, and my task is to introduce Vladimir Voevodsky. So as a relatively large number of mathematicians in this country, he was educated in the former Soviet Union. He was student of Moscow State University from 83 to 89, then came to this country, got his PhD at Harvard in 92, was at Northwestern University from 96 to 99, and then he had some nice collaboration with Suslin. And then he came to the Institute first as a member in 98 and became professor here in 2002. So he has been able to successfully introduce methods of homotopy theory in algebraic geometry. And for me, this is somewhat like mixing water and fire. Objects of algebraic geometry are very rigid, with very few maps from one to another, while objects of homotopy theory are very flexible. And it looks hopelessly naive to try to mix the two together. But that's what he has been able to do. For me, a first example was this extraordinary paper with Suslin, where it's clear that you cannot imitate the definition of homology using simplices in algebraic geometry just by using algebraic map from simplices to algebraic varieties. But what this paper shows is that if you allow finitely many valued maps instead of plain maps, then you can perfectly imitate the definition of simplicial homology using this kind of algebraic simplices, at least for Thorson coefficient. The integral coefficient is hopeless anyway. Then he has also been able to use idea of homotopy theory to obtain a good triangulated category of motifs, hopefully good, and has been able to use such tool to prove extraordinary results about Galois cohomology, so cohomology for Galois group of field. First, he proved this is related to mod 2 cohomology, the Milnor conjecture about its structure relation with Milnor K groups, and for this he got the Fields Medal in 2002. And then more recently, with some geometric input from Rost, he obtained similar result for all primes, so about Galois cohomology of field. And now his interests are in another direction, another improbable mixture, here homotopy theory, formal language, automatic verification of proofs, things which seems to have not much in common. His title today is What if current foundations of mathematics are inconsistent? And I am very curious to hear what he has to say.
Hello, and thank you everybody for coming to my talk. I'm quite nervous because the subject is such a controversial thing. So I'll try to do my best, and I'll try to explain what I mean by current foundations and what I mean by their possible inconsistency. So, but I'll start with a few historical, actually, comments. So we are celebrating these days the 80th anniversary of the Institute for Advanced Studies, but we could actually be also celebrating the 80th anniversary of something else, which is probably even more momentous than the foundation of the Institute for Advanced Studies. As it happens, it's almost exactly 80 years ago that Gödel Gödel came up with the proof of his second incompleteness theorem. What we know, we don't know, of course, the exact date when it sort of crystallized in his mind. But what we do know is that when he was presenting the proof of his first incompleteness theorem on September 6, 1930, he didn't know about the second incompleteness theorem. And when he submitted an abstract of his final paper in October 23, 1930, he already knew about the second incompleteness theorem. So it happened somewhere between September 6 and October 23. So it's like we're almost right in the middle of that period 80 years ago. So let me formulate his second incompleteness theorem in the following form, which might look a little bit too strong for some who know the original formulation, but I'm going to argue that that's how it really should be understood. So the theorem says, in my understanding, is that it can be proved that it's impossible to prove consistency of the first-order arithmetics, elementary number theory, or of any other theory which is at least as strong. Now, von Neumann commented on, von Neumann somehow understood that Gödel's first incompleteness theorem, which spoke about just unprovable statements in arithmetic, implied the second, and he wrote to Gödel the following interesting words, that thus I think that your result has solved negatively the foundational question. There is no rigorous justification for classical mathematics. And that's von Neumann to Gödel on November 29, 1930. Again, 80 years ago, pretty much. So, so let's see how things kind of developed after that. So Gödel himself, I'll come to it in the next slide. But okay, let me first say that. So we have like something which I'm choosing to call Gödel's paradox. So on the one hand, we know, and I probably should have put quotes around this "know," that the first-order arithmetic is consistent. That's the commonly accepted fact among mathematicians and as a consequence among everybody else. On the other hand, it can be proved that it's impossible to prove that it is consistent. So we have these two statements, and I should tell you, if one really thinks deeply about it, this is extremely unsettling for any rational mind. It's and what one comes to is that, so what are the choices in resolving this paradox? And there are three choices. Well, aside from, well, there are three choices. So the first choice is that if we know that it's consistent, then somehow we should be able to come up with a proof. And then the Gödel theorem, the second incompleteness theorem, as it been stated before, is incorrect. That is the choice which was essentially made by 90% of people who were seriously working on the subject. So it was the choice, I think, made by Gödel himself, and it was a choice made by many others. So there was many attempts to still kind of prove that the first-order arithmetic is consistent despite the Gödel theorem, and somehow circumvent this theorem in one way or another. And I will speak about such attempts in a few minutes. So there is a second possibility, which is which we can admit that there is some kind of transcendental knowledge which humans can obtain which is correct, but not just cannot be rationally kind of supported, but it can be proved that it cannot be rationally supported. And that choice have been also made by many and been a source of a really large body of dubious philosophical texts, I would say. And well, dubious is, of course, my own personal opinion. And so the third possibility, which is the least considered one, so to speak, is that we can admit the fact that our convention that we know that it is consistent is actually an illusion in this case, and that the actual formal system of the first order arithmetic is inconsistent, and that's what the proof means. And I want to discuss this third possibility today, because I think that it is time to consider this third possibility very, very seriously, and to and that's basically the only choice which is left, because so many efforts were made to try to justify the first choice, and they were all unsuccessful. The second choice seems to be like, I personally don't want to talk about it much. And so we are only left with the third. And so let's consider it as a serious possibility and see what consequences it might have. So first, let's see what kind of arguments do we have in the support of this knowing of the consistency. And in the process, I'll outline what consistency actually means. And inconsistency of first-order arithmetic doesn't mean that 2 plus 2 doesn't equal 4. Please don't worry. It's something much more kind of. It really has nothing to do with the validity of the usual computational mathematics, which is being used all around us. And if arithmetics is this first-order arithmetic is inconsistent, it doesn't mean that planes start falling from the air or bridges start falling down. No, it's mathematics, constructive. Well, the actual computational mathematics is supported by much more than our belief in consistency of a formal theory. So anyway, so the two mathematical arguments are in the support of the consistency of the first-order arithmetic as a formal theory. Standard two are as follows. So the first one, I'm calling it formulas as subset interpretation of first-order arithmetic, and I'll explain what it is. And the second one is a proof given by German logistician Gentzen at the end of 1930s. And this argument uses induction on the length, on the structure of the proofs in arithmetic to show that one cannot obtain a proof of absurdity. And I will show what both of those mean. So first of all, what is the first-order arithmetic? And what does it mean by its in or consistency? So the first-order arithmetic it's not a collection of rules for operating with numbers. No, it's something entirely different. It's a mathematical object which belongs to a class of mathematical objects which are called formal theories in first-order logic. And a formal theory is specified by a collection of data of the following form. So it's specified by two alphabets, one for special symbols and one for names of variables. There are certain rules which I'm calling syntactic rules, which determine what sequence of letters from both alphabets which actually specify for a given collection of names of variables, it specifies which sequences of letters from both alphabets are grammatically correct formulas in these variables. And these syntactic rules are such that it's easy to verify. So if one given a sequence of symbols from both alphabets, then doing some simple verification algorithm, one can determine whether it's a grammatically correct formula or not. Then there are deduction rules. So there is a notion of a closed formula. Closed formula is a formula with no free variables. So the number of free variables is 0. So there are deduction rules which are certain operations on closed formulas. So it's certain ways to combine some closed formulas to obtain a new closed formula. They're kind of combinatorial rules. I'll come to it in a moment again. So the first component of a formal theory is a collection of kind of initial closed formulas, which are called axioms. So we have this kind of a combinatorial game, a Lego, I don't know, where we have some initial pieces, and we have rules by means of which we can form new pieces out of these initial ones. And anything which can be formed from these initial axioms by means of these deduction rules is called a theorem. In principle, this is an extremely general definition, and one can have formal theories in that sense which have no meaning other than just some combinatorial rearrangement of symbols. But typically, they're being used to formalize some fragments of natural reasoning, and it's done as follows. So a series of first-order logic form a subclass of among all formal theories, and among their special symbols, there are these 6 standard symbols of first-order logic, which every mathematician, I don't know if they're learned at school in any way, but definitely learned by any mathematician. So the first few are called quantifiers. It's for all and exist. So excuse me, for all and exist, I should say something about it. So these are symbols, this inverted A, inverted E, and this little v, and this little inverted v, and these six things are symbols of the special symbol alphabet. Now, what's written on the right from them in quotes, these are translations of these symbols into natural language. So this is not a part of formal theory at all. It's something external to the formal theory. It's some rules which allow one to translate formulas of the formal theory into sentences of natural language. So here the rules are such that this inverted A is translated as for all, inverted E is translated as there exist, and then there is or, and, implies, and not. There are also parentheses and I think usually a period, which are used as punctuation marks in the formulas. So a first-order theory is called inconsistent. If there is a closed formula such that closed formula A such that A is a theorem and also not A is a theorem. So the formal system of arithmetic contains among its special symbols also symbols for 0, 1. Well, there are actually several different versions, but like one of the standard ones, it would contain additional symbols for 0, 1, addition, multiplication, equality, and let's say the greater sign. So again, these are special symbols, and when I'm saying that it's equality, it means that that's how I translate the appearance of this special symbol in the formula into natural language. So that's an example of a closed formula, and that's its actual form. It's just a sequence of symbols from this alphabet. And what is below is its translation into natural language. It translates into for all n there exist m such that, and then there is some arithmetical expression. Oh, interesting, actually. So that I've corrected it. Yeah, thank you. There should be, as stated here, this sequence of symbols represents a syntactically incorrect expression. So for it to be a syntactically correct closed formula, one has to put an n between the star and the plus, and that's my typo. So closed formulas can be translated into English as statements about natural numbers. Formulas which are not closed, so which contain free variables, as it's called, can be translated into English as descriptions of subsets in the set of natural numbers, or more generally in the set of sequences of natural numbers. So for example, if I remove the very beginning of the first formula, so instead of writing for all n, I'll just remove this for all n, just considers this. So this says there exists m 3n squared plus 5m squared plus 7 equals 17mn. So one interprets it as a description of the subset of natural numbers, which consist of natural numbers n, such that there exists m, such that this equation is satisfied. If I had more than one free variable, I would have a description of a subset in the set of pairs of natural numbers. Now, the deduction rules, as I said, are just formal combinatorial rules to operate with these sequences of symbols. They're kind of, you have one sequence of symbols which satisfies some condition, you have another sequence of symbols which satisfies some condition. Then you can kind of permute them in a certain way and do certain things with them, and you get another sequence of symbols which is said to be deduced from the two previous ones. And those combinatorial rules are chosen in such a way as to reflect the usual natural deduction rules for statements, in this case about subsets of sequences of natural numbers. So for example, if there is a statement that for all n something holds, and then there is a statement that there exists n that something else holds, then from this I can deduce that there exists n such that both the first something and the second something holds. I can do it using one of the formal deduction rules. So now so going back to the definition of a formal system, one starts with the axioms, which is a collection of statements which are kind of verifiably correct, so which, when you translate them into English, they map into something which is true about natural numbers. And then there are deduction rules, and using these deduction rules you get many, many more statements which are also supposed to be true, because on each step you use the logical operation which should make a true statement out of other true statements. Now that would make perfect sense if each formula actually had kind of material meaning in a sense. What happens in arithmetic is not that. There is a serious problem with this interpretation. So this interpretation of formulas as subsets was, of course, the original source for the certainty that arithmetic is consistent. And in fact, it was, I suspect, the source of the original formulation of formal arithmetic as it was. So the problem here is that the subsets which correspond to general formulas are really not, are really totally surreal. They are, it can be proved that there are formulas like, let's say, with one free variable. So a formula with one free variable will describe a subset of natural numbers. But one can prove that there are formulas with one free variable which describe a subset for which it's algorithmically impossible to show not for a single number whether it belongs to this subset or not, or doesn't belong to this subset. So it's a subset about which you can prove that it's impossible to say anything about this subset whatsoever. So using this kind of objects as intermediate steps in logical, in chains of logical conclusions, I find it inconvincing as an argument for consistency. So that's my critique for the first argument in the support of this no. Now, speaking of the second argument in the support of the no, it's the Genson's proof. Unfortunately, I cannot explain it in much detail here. What he does is he considers this as a formal system, and no interpretations are assumed. And he considers the structure of the deduction sequences, so to speak. And each deduction sequence can be assigned kind of something like a collection of trees, finite trees. Trees, I mean, in mathematical sense, so kind of combinatorial objects. So one can assign a combinatorial object which measures the complexity of the deduction process. And then one can one can present an argument which uses induction on this. So these combinatorial objects are called ordinals less than epsilon 0. And one can give a definition what does it mean for two ordinals to be one less than another. And that's all quite constructive. And then he shows, Genson's proof is that if there is a proof of contradiction, if there is an inconsistency in formal arithmetic, then there would exist a sequence of these ordinals which is decreasing at each step but never terminates. So an infinite decreasing sequence of these ordinals. And then he and then there is a certain argument, I would put it quote unquote, which then he says that that's unlikely. I mean, or rather, it's something like he says that it's self-evident that that cannot happen. So this self-evidence is extremely suspicious because in a complete agreement with Gödel's theorem, one can show that it's impossible to prove using the usual induction and usual enumeration techniques that any such decreasing sequence terminates. So it's impossible to prove using the usual reasoning means that it terminates. The only reason to say that it terminates is to declare that it's self-evident. So that, again, is not very convincing. So, so basically what it means is that if we find inconsistency in the first-order arithmetic, it will mean that there will be this non-terminating sequence of ordinals less than epsilon 0. So what? That's an interesting conclusion, but it's not earth-shattering in any way. So here we come to the second part of our investigation in terms of what such an inconsistency would imply. So the first part was kind of So there are these arguments in support of consistency. Let's look at them carefully and see. So assuming consistency, let's look at this argument, and don't we get some sort of a really obvious contradiction? And I'm arguing that no, we don't get any obvious contradiction. We get that certain things which look self-evident to which looked self-evident to some people will turn out to be false, but these things have absolutely no material meaning. I mean, these are things which can be neither verified nor falsified by any sort of an experiment. So these things are purely surrealistic, and so can be either false or true with no problem. But let's see what it will mean for mathematics, because that's of course something which on the mind of any mathematician who starts to consider such a possibility. So first of all, inconsistency in the first order arithmetic will mean inconsistency of almost every other foundational theory in mathematics, standard foundational theory in mathematics. So it would mean inconsistency of set theory in particular, or of all kinds of flavors of set theory. What is a little less known but also true is that inconsistency of classical first order arithmetic implies inconsistency of so-called constructive or intuitionistic arithmetic, and that has been shown by Gödel himself in 1933. And that's a purely formal proof which takes a proof of contradiction in classical theory. So the difference for non-mathematician, non-logician, the difference here between classical and intuitionistic is that intuitionistic doesn't allow for, it doesn't include the rule that a double negation of a proposition equals the proposition. So in classical case, one has the rule that the double negation of a statement is equivalent to the statement itself. In intuitionistic, this rule is excluded. However, one can show that as far as the issue of consistency is concerned, it doesn't change a thing. So if we find inconsistency in the first order arithmetic, then all of those theories are then we'll be able to construct inconsistencies in all of these theories as well. So what should we do about it? Because I'm quite seriously suspecting that such an inconsistency can at some point be found. As I said, because of these only three choices there, and one of them must be true, and the first two are unlikely to be true. So well, actually, as far as the transcendental knowledge is concerned, I want to point out that while I may admit a possibility of such knowledge concerning things natural in a sense, such a thing as the formal first order arithmetic is totally a creation of human minds. And there's absolutely no reason for transcendental forces to kind of ensure its consistency by transcendental means. So the Gödel argument, in fact, is general enough to basically show that so if the first order arithmetic is inconsistent, it makes little sense to try to find foundations which are consistent. Any foundations which are rich enough to be useful for the formalization of kind of abstract mathematical thinking which we are so fond of, any such foundations will necessarily be inconsistent if the first order arithmetic is inconsistent. So the only possibility here is that we mathematicians will have to learn how to construct reliable proofs using inconsistent formal systems. And I think it is possible. It's entirely not. It's not easy, and it's. But I think it is possible, and it is emerging. such a possibility is emerging for the kind of foundations which are now being developed, which are based on ideas which are coming from theoretical computer science mostly at this time. So one possible candidate for such, so we need new foundations which will be formulated in a formal system which allows one to, which can be used despite its inconsistency or possible inconsistency, can be used to construct reliable proofs. So the classical first order logic is not good at it, because if it has an inconsistency, then one can prove everything, and it stops being informative. However, there are other types of formal systems which can be used for formalization of mathematics, which react to inconsistency in a much less drastic way, in a sense. So inconsistency in such systems doesn't mean that the system totally becomes totally uninformative. And one of the examples of such classes of systems is the class of so-called constructive type series. So that is a class of formal systems which have been used extensively for in the theory of programming languages. It's rather standard, it's becoming rather standard thing which theoretical computer scientists may learn about. And what is important for us is that, well, they have many interesting features which I don't have time to speak about, but what's important is that a proof in such a system, a proof of a formula in such a system is itself a formula in this system. So a proof is not something external to the statement, but to the language. It's not like there are no deduction rules per se. There are only syntactic rules. And proving a statement means constructing a syntactically correct statement of a certain form which includes the original one. It's kind of extending in a certain way. So a proof becomes an object which can be studied inside the system itself. And so if one has an inconsistency, for example, so one has a proof of A and a proof of non-A, then one can show in many systems, of course not in any, in many systems that any such proof can be, well, it sort of can be detected. I mean, the proofs which lead to inconsistencies have certain negative properties which can be determined by an algorithm. So, so what might be possible, and here that becomes a bit of a fantasy because it's very much kind of recent activity, so to speak. So what might be possible is the following type of workflow, which in constructive type theory in particular is possible. So we take a mathematical problem, we formalize it. We formalize it in a language which allows all kinds of abstractions and which is probably even more powerful than our set theory which we're using today, and it allows for more abstract steps to be performed and more abstract ideas to be used. So using this formal system, we create a solution of the original problem, and that's the creative part which will always remain creative. There is no danger about that. Then this proof is submitted to a verification algorithm, which, well, we're already assuming that the proof is kind of syntactically correct, so it's logically correct. But then there is a verification that it's reliable in a sense. And this verification will not be, as examples show, such a verification algorithm, we will not know whether it terminates or not in general. So if it terminates, then the proof is reliable. If it doesn't terminate, then we know nothing. And it means that we probably have to look for another proof for which algorithm will terminate faster. But also there is the idea that most proofs which one constructs in such a way are reliable. So it doesn't happen often that it doesn't terminate. So that's kind of a more technical comment about how to ensure reliability of a given proof term, and that there are probably different ways. I mean, I'm sure there are different ways. Like the simplest one which comes to mind is that the solution is reliable. So there is a proof term, apply normalization procedure to it, and if after normalization it lands in the subsystem for which consistency can be proved, so kind of all our abstract thinking kind of cancels out in the process of normalizing the proof, then we can rely on it. And if it doesn't, then it's not so clear. So so I want to summarize, because the schedule for this talk was, I was told to have a shorter talk and longer session for questions and answers, because the summary here is as follows. So first of all, I suggest that the correct interpretation of second incompleteness theorem is to consider it as a step towards future proof of inconsistency in the mathematical, in the formal systems which this theorem refers to. And that is, of course, purely a conjecture. You can say that it's I'm making this as a conjecture, and it would be wonderful if we could find the actual inconsistency, because then we would kind of know where that would provide us with a huge amount of new knowledge and understanding. But I don't know when that may happen, but even just having in mind that this is a really interesting problem to consider, I think is very important. So such an interpretation definitely cancels out a lot of dubious philosophical noise around Gödel's theorem, which I think would be very good. And as far as mathematics is concerned, and so if there is indeed an inconsistency in the first order arithmetic, it would mean inconsistency in basically any sufficiently rich foundational system. So in mathematics, we will that's my idea. That's the only thing the only kind of solution which comes to my mind is that we may have to learn to use inconsistent systems to obtain reliable proofs. And ultimately, if we do learn to do such a thing, it will be very liberating, because then one can use reasoning systems which are known to be inconsistent but which are closer to our intuitive thinking to construct proofs which can then be verified formally to be reliable. So ultimately, it can lead to more freedom in the mathematical workflow, so to speak. There are also some important speculations one can do concerning the changes in mathematics which it may lead to, and how it relates to the existing troubles between mathematics and physics and stuff like this. But that would be more. That would rather be a subject of a separate talk. So for this talk, what my main intention was to attract everybody's attention kind of seriously to the possibility of such an inconsistency, and to argue that such an inconsistency would not mean the end of the world, but rather a liberation of a lot of our thinking in mathematics, and it may have a lot of constructive and positive consequences. Thank you very much.
So we have time for questions.
In your three alternatives at the beginning, you left out the alternative which most of us believe in, that we
That's all right. That's definitely acceptable. But when one hopes for something, one also allows for the possibility of the opposite. So as long as it's not kind of I know is consistent and nothing else is ever possible, any other kind of intermediate situation is I think, a personal choice in a sense.
Can you anticipate inconsistencies also in physics? Well, in one statement says something that two theorems which cannot be proved from the foundation. How does one know the truth can be proved? One circumstance, I think, occurs to one. Goldbach conjecture, for example. You know, he made this conjecture in 1742 or whatever. That every even number can be expressed as a sum of two factors. Now, no counterexample, as far as I know, has ever been found. Suppose it is the case that no counterexample will ever be found, and yet it may not be able, one may not be able to prove it from the foundation. So here you have a theorem which cannot prove, or something like that. I don't know.
Yeah, well, there are many such things. I mean, there can be many, we know it from Gödel's own work that there is the first incompleteness theorem, which says that there are multiple statements which, in any formal system, there will be, in any consistent formal system, there will be multiple statements which cannot be proved from the axioms. That kind of, that doesn't bother me in any way at all. After all, the question of proving or unproving Goldbach conjecture is, I mean, okay, no, that's all right. That doesn't bother me. So I'm sorry, yeah. So what was your question?
Do you anticipate such inconsistencies also in experimental sciences, where you can do an experiment and verify what's true independent of what our imagination dictates?
Well, there can be no inconsistency in experimental science. There can be only results of an experiment, by definition. So inconsistency is when what you think is not what actually happens. That's inconsistency. And so no, I definitely consider the material reality as the kind of absolute judge of truth, and so there can be no inconsistency in experimental. I don't know what is an inconsistency in physics. I mean, what is inconsistency in formal arithmetics, I have explained very concretely. I don't know what is an inconsistency in physics.
I know you said it was essentially for another lecture, but could you just give us... although you said this would be properly in another lecture, which hopefully we'll get the chance to invite you to give, I would just wonder if you can offer any thoughts about how analysis, our concepts of real numbers and so on, might be different if the usual foundations are inconsistent.
So first of all, for that we don't need them to be inconsistent. It is entirely possible that our understanding of real numbers is not an adequate formalization of the notion of continuity, and that possibility is quite real even without any inconsistency. So this inconsistency here is unnecessary for this side of the story to develop. And the notion of real numbers, as many, I think as many different observations kind of show, mind observations, the notion of real number seems to be over-idealized in a sense. So it's an over-idealized object which and it's clear that this over-idealization was necessary in order to make reasoning about real numbers simple enough for it to be humanly practical. And it's quite possible that in years to come, because of this development of the computer-assisted thinking, let's put it this way, especially about mathematical objects, maybe we'll be able to explore other possibilities in which the notion of continuity will be formalized in a less idealized way, and so will allow for and which will then avoid some of the physical paradoxes. I mean, some of the physical paradoxes, so to speak, which one encounters when one tries to use the usual notion of continuity to describe the physical reality, and together with the notion of locality, one gets into this stupid situation where, in order for something at all to happen, two real numbers have to be precisely equal at some point, and which of course can never happen. And but this line of development does not require any inconsistency. It can be, and it will proceed, I'm sure, independently on that.
Can I summarize what you're saying as follows? Even if the usual foundations are inconsistent, are consistent, there might be a better theory of real numbers. Is that what you're saying?
There might be a better way to, even if the usual foundations are consistent, there might be better foundations, first of all. And second, even in given foundations, there might be a better way of formalizing the concept of continuity than the current one. But I would rather go for new foundations and new formalization of continuity in new foundations as the prediction.
So I just wanted to make the comment or raise again the issue of whether experiments are, results of experiments are consistent in the sense that it's almost impossible to think about the results of an experiment without putting some kind of interpretation on it. Even if the interpretation is simply that the experiment is generalizable, that's already an interpretation. And we have, experimental truths that have, in a sense, been falsified at the Institute, like velocities add and so on,
like what?
That velocities add, that, turns out not to be true in special relativity, but yet for centuries it appeared to be experimentally incontrovertible. That's just a simple, I could think of other examples, but, we make a measurement, there's always some limitations of how we're observing it, and we assume it's generalizable. We don't really know that. We put all kinds of interpretations on it. I would almost, it's hard for me to figure out which is more unprovable, an experiment or a mathematical theorem. I don't know if others want to comment. But
which is more?
Which is more unprovable?
Well, experiment is well, there isn't really a notion of a proof for an experiment. There is a notion of proof for a mathematical statement if it's formulated in a particular formal system. There is not a well-defined notion of, it's not clear what it means to prove an experiment. I think, there is this, it is, one can argue that it is true that, because of the quantum mechanics, for example, there is a possibility that we all right now just float in the air, because even not quantum mechanics, just random movement of our molecules will suddenly all coincide in direction and will all move, start floating in the air. And there is a certain probability for that to happen. And that because of that, the gravitation that would falsify the gravitational laws which explain why we're actually not floating. So the argument against such an argument is that there is I like to use the expression gap and scale. there's like a huge gap in scale between the probabilities involved in all of us floating in the air and all the probabilities with which we are dealing in any kind of experiment or prediction or anything like that. And so this gap in scale and probabilities is so huge that it permits us to speak of one of those things as to be simply impossible. So that's about proving an experiment. Right? I mean, you're right. I mean, there are all kinds of things which may happen with very, very low probability, which you might have made an experiment and like measured something, and that something been constant for a year, and then or 10 years or 20 years, and then you can say, okay, there is still a little probability that in 5 seconds after that it will totally change. Yes, there is, but it's not practical to take such a probability into account. It would so. Pierre, I think you should be moderating. So you
One of the great things in physics is nothing is absolute. If you have something you believe, you always accept the possibility that it may change. And so physics is somewhat temporary knowledge. But could this happen in mathematics? Could you get to a certain state where you sort of believe some things, some mathematical truths, but you entertain the possibility that they will later be disproved and something replace it? Mathematics tends to be absolute, but maybe it's not.
Mathematics is, yeah, it has been historically kind of static. I would say, instead of absolute. So if something has been proved, it's been proved forever. And one can speculate about a possibility of kind of dynamic mathematics in that sense, but I think there's again a gap in scale between this and even the inconsistency issue. I mean,
well, the more complicated mathematical theories could be that. You could have
it's very hard to imagine at this point, and
but
it's harder to imagine that inconsistency of arithmetic.
Just say there are many historical examples of theorems which were accepted and later found to have false proofs.
No, but this is simply a wrong proof, and that's what the computers are here for. So,
So I'm afraid it's time to conclude. So I would like to thank Voevodsky for his lecture.
Thank you.